times the derivative of the bottom over the bottom squared.
Right.
Okay, so now the top, we do need to simplify. I'm going to simplify it above that because I don't want to have to rewrite all this, but it's 2x cubed minus 2x minus 2x cubed minus 2x. So it ends up being, not too bad. It ends up being minus 4x over x squared minus 1 squared, like that.
Okay.
All right. So that's the first derivative. Now you got to take a second derivative, f prime of x. So the next derivative, still quotient rule. It's the bottom times the root of the top minus the top times the root of the bottom, which is a bit more involved, but you can follow that if you want over the bottom squared. So it's now the power of 4. This requires a much more sophisticated algebra. You have to see that you can factor out an x squared minus 1 from both. So you end up getting x squared minus 1 times negative 4. And then we got some signs going on here. I'll try to do that. So it's positive 4x times 2. That's 8x times that is 16x squared. And then it's on the bottom here. You got the x squared minus 1 to the 4th. So you can see that one of these cancels one of these to get you 3. This is minus 4x squared plus 4 plus 16x squared. So in the numerator, it ends up being 12x squared plus 4 over x squared minus 1 to the power of 3.
Okay.
Now I don't know. Like in the real world, even in engineering, no one like ever asks you to take a derivative or something like that. So I mean, and I'm tired. I'm gonna type this into one of these wonderful calculators that exists on the internet where they're driven by computers that do not make mistakes. And let's see if I can get the second derivative here out of this. So unfortunately, they don't always give you like a nice derivative. Like sometimes you don't like the output. So this is correct though. And then I'll take the derivative of that. Sometimes you kind of got to work with these things. I don't know if you've done anything like ChatGPT, anything like
Yeah,
that.
I have.
You just got to be careful there that you actually like know. So this is correct here. So you set this equal to 0, the second derivative, but you only need to set the numerator equal to 0. Here's why, because the numerator is where these zeros are going to occur. So I don't know, fortunately, unfortunately, the numerator never equals 0 because of the plus that's in the middle.
Right.
Okay, so there's no there. So you might think, well, there's no critical points. That's true. There are no critical points, but this is a big but. You also have to look at the domain. So the domain comes from the original function, the original function here. Is there any places where the bottom is equal to 0? And the
No.
answer is yes. Yes,
Oh.
because it's difference of squares. It's at 1 and -1 that it's undefined.
Oh,
So,
okay. The original. I was looking at the f prime of x.
yeah. Yeah. So now you actually do have to test these points. So this is your second derivative right here. And you want to test something in each region. So 0, -2, and 2. Like that. And now you test it in the second derivative. So right here. And again, it's not about a number. It's about whether it's positive or negative. So could you put these three numbers, -2, 0, and 2, back into this line and figure out whether it's positive, negative, or positive in here? I'm going to step away for 30 seconds to grab my coffee, and then we'll be right back. All right, you have anything for me here?
Okay, so -2, I got -52/27.
You're trying it in here, right? In the second derivative.
Yeah,
So the numerator should be positive. If you're squaring a negative, that's positive times 12 is positive plus 4 is positive.
dang. Okay, that's weird. Hold on. Yeah. Yeah, I don't know why it's giving me a negative number. Let me try that again. Hold on. Yeah, I'm still getting a negative number. I don't know why.
Right. I don't know what to suggest, but it can tell you for sure that it's going to be positive up top.
Yeah, no, I see that. I don't know. My computer, my calculator is just messing up, I guess.
Well, make sure you're putting it in parentheses. Like the last thing you want to do, it's parentheses 12 -2 squared plus 4 slash parentheses. I mean, I don't know what kind of calculator you're using, but you have to like it doesn't know unless you tell it that
Yeah,
that
no, it's in parentheses. That's why I'm confused. Like I wrote it exactly how you have it on the thing. I don't know why. It might just have to be reset. I might just reset it because
Okay, so the first one ends up being positive, second one's negative, and the third one is positive. Now, the other way to get this, I know this is a lot of work to what we just did, is you could always just graph the original, and maybe you notice this stuff without having to do all this. Like, but there's then there's no work to be shown either.
right.
So that's your call. So we would say concave up from -infinity to -1, comma 1 to infinity, concave down from -1 to 1.
Okay.
So you where should we go from here?
Um, number 15.
Okay. All right. So nice thing here is they've given you a window that you're not looking. You don't have to. We had that weird problem yesterday where it was if they don't give you a window
Right.
region to bound it in, that's really bad. So first derivative here is 2. Derivative tangent is secant squared x. And you got to take a second derivative. Derivative 2 is 0. Derivative secant is -2 secant x. Derivative secant x is secant x tangent x. So you should get something like this.
Yep.
And then you can rewrite it if you want secant squared x tangent x. So this goes to like, do you remember your trig? Do you remember like, can secant ever be 0? Like it's really like, it's like, does secant squared x equal 0? Does tangent x equal 0? And the answer is secant squared does not equal 0. The graph of it is a bunch of u's because it's squared, they're always positive. Tangent does. Tangent has that snake thing. I think it's that. So it does equal 0. In fact, it equals 0 when x equals 0. And that comes from unit circle. Comes from everything tangent at sine x over cosine x. You're really asking where does sine x equal 0, which is at at 0. So you have a critical point, or sorry, a possible inflection point at 0. So your number line, though, this time is from minus pi over 2 to pi over 2. It's not forever. And then it's 0 is that possible. It's not a critical point, it's an inflection point, if it is anything, or maybe an inflection point, I guess. So this is where it gets really hard to you have to be able to test points in here. So the most reasonable ones are like pi over 4 and minus pi over 4.
Okay.
All right, so now we're testing them in the second derivative. So up here in the -2 secant squared x tangent x. So we really want to break this apart to understand the whole idea of, I guess because you have a calculator, you could do it this way, but the -2 is always negative. The secant squared is always positive. So it comes down to what tangent is. What's tangent of pi over 4? It's 1 or it's positive. So you have a negative times a positive, which is negative. The tangent of minus pi over 4 is negative. So you have a negative times a positive times a negative, which ends up being
Positive.
positive. Yeah. So there you have it. It's concave up here, concave down here.
Okay, perfect. I do problem 21.
Sure. All right, almost there. Everything is taking longer than it should. Okay, here we go. 21. F of x equals x times x minus 4 cubed. And we're trying to find the point. Okay, so I actually need to go back to the previous problem. This is an inflection point. So an inflection point occurs. Sometimes it'll say IP for inflection point. An inflection point occurs when the second derivative goes from plus to minus or minus to plus. Okay.
Okay.
It's kind of like the other ones. When you go plus to plus or minus to minus, it's nothing.
Right.
Good to have on a reference sheet.
Yeah.
Right. Why am I doing that? Okay, so we got to go take a derivative. Ugh, these are horrible. The derivative is first times the derivative of the second plus the second times the derivative of first, which is 1. You can factor out an x minus 4 to the power of 3 from both. Sorry, 2 from both, and you end up getting 4x from the first one plus x minus 4 in the second one. And the reason you do this is because when you have to take another derivative here, 4x plus x is 5x minus 4. If you have to take another derivative, well, you want to simplify
Right.
this because it makes taking the next derivative even easier.
Yeah.
So yeah, we're only halfway there. We got to take yet another derivative. So second derivative here, first times the derivative of the second plus the second times the derivative of the first. And then you can see they both have an x minus 4 in them, so you factor that out. And then you have this x minus 4 times 5 plus 5x minus 4 times 2. And then you do want to simplify. So you got 5x minus 20 plus 5x minus, no, sorry, 10x minus 8 So it looked like it ends up being x minus 4 times 15x minus 28. Does that look right?
Yep.
No, 30x, no, 15x. Okay. And I really should check this because I don't know. I don't know that I'm all the way there. So let's with this, let's do x minus 4 to the power of 3. Is that what I wrote? That doesn't look right. Did I not write this? I made a mistake somewhere. Oh, this was supposed to be a 3. So I messed this up real bad. I apologize. So
That's okay.
disregard everything I just did. And the first derivative is 4x minus 4 squared times x minus 1. And then the second derivative will be coming up here. I was surprised that it wasn't nicer because this is a classic exam problem. So then the second derivative is 12 times x minus 4, x minus 2, like that. So you set this second derivative equal to 0, and you can see that there are 2 places to test. X could be 4, x could be 2. So those go on your number line.
Okay.
So what I'd like you to do is test points in each region, 0, 3, maybe 5, and you're testing them in here, and we only care whether it's positive or negative, so you can get a number out if you want, but I only want to know whether it's positive or negative, please.
First one is positive, so 0 is positive, 0 to 2 is positive. Um, 4 is 0.
You cannot test you can't test
Oh,
that's why
no,
I
yeah,
said make sure you put your test points in a different spot so you don't think to try them.
yeah. 3 is negative. Five is positive.
So x equals 2 and x equals 4 are both inflection points. Okay, that's a test question you'll get. But they'll ask for more than that. They'll ask you to put the 2 and the 4 back into the original. They want both ordered pairs of the inflection points, x and y. They don't in this problem, but that's, oh, it actually does say find the points of inflection. Sorry, I didn't even notice that. So you actually do have to do this. You have to put these back into the original. And why don't you do that for us? I'll put the original here. So you want to put x equals 2 in there, x equals 4 in there, and see what you come up with.
2 is negative 16. Four is 0.
Yeah. Good. Okay, so those are the inflection points. Again, if it goes from plus to minus or minus to plus, it is an inflection point. It is not always alternating in sign. Don't make that mistake of thinking it always does that. It may appear to be that way, but you know what they say about assumptions. So just be careful with that. It's concave up from minus infinity to 2 and 4 to infinity, and concave down from 2 to 4.
Okay. We do 23.
Sure. All right. Why don't you try taking the first derivative of this for us?
Is it just x plus 3 to the half?
Is your final answer? It's product rule, like it's right down the middle. It's a
Oh,
product.
right, okay. Is it 3 times x plus 2 over 2 root x plus 3?
Like this.
Yeah.
Okay, let's take a look here. So it's the first times the derivative of the second, which is what you were alluding to. It's 1/2 square root x plus 3 plus the second times the derivative of the first, which is 1. Now you got to be careful here in terms of like, do you want to combine like terms? And you probably do. I'm not sure exactly. Like, do you want to make it as a common denominator or not? Is that what you did to get your answer?
Yeah.
Okay. Um, yeah, you probably do. These are awful. I mean, these are like the worst kinds of problems because you don't even know whether you should do that or not. So it ends up being here, like you said, you get two. Well, I got some 2x plus 6. That's what you have here. So you end up getting x plus 2x plus 6 over 2 square root x plus 3, 3x plus 6. Yeah, so it's exactly what you said there. So now you have to take another derivative, which I get kind of worn out doing these. Um, you do have to be able to do them. You just have to realize that you may not want to spend all your time preparing for this by taking a derivative. Like you don't want to spend all your study time doing derivatives. So maybe do the first one. But here's the second derivative, like this. And
Okay.
let me see here. So you set this equal to 0. And it's kind of like when we it's kind of like the one where you do have to set the numerator equal to 0. So x plus 4 equal to 0. So x equals -4. That's that is like not necessarily, it's not a critical point. Critical points are for the first derivative. It's a place to put on there, but you also care about where the denominator is equal to 0. You care about where the fact that this -3, that x plus 3 could be 0 as well. So you have to break that. You have to have that issue as well. So you got to say, okay, there's -3, sorry, -4 and -3. And you really have to test those three regions for this. So again, you're testing it in the second derivative, this thing up here. Like that.
So I should just pick numbers and then test it.
Yeah.
Okay.
The other thing is, again, like you could look at the graph. Like now that you have the critical numbers, you could go back to the original and graph this,
Right.
and that will essentially tell you what you're looking for.
Yeah.
Oh, I'm sorry. And the other issue here, no, I'm sorry. There's another issue. I didn't even look, I wasn't looking very carefully. The domain, this is not correct for this number line. The domain is that it's all the numbers greater than -3 to infinity. The reason is because that square root of x plus 3. So you have to set that part greater than or equal to 0. So x has to be greater than or equal to -3, which means that this -4 doesn't even matter. You're basically just over here testing stuff, and you'll find that it's concave up here. I'm going to snip in the graph. So it's really a combination of your calculus, algebra, and graphing to make these decisions. Here's the graph. You can see that that's concave up
Yep.
everywhere.
Okay. We do 27 next. Or that one's similar to the other one that we did, right?
Almost there. You said 27.
Yeah.
Is it the same instructions?
Yeah, I believe so. Let me just
Yeah.
double check that.
Okay. So the previous one we did does not have an inflection point. I'm like beating around the bush to get to the actual answer. Like this one does not have an inflection point. It's always concave up, or it's always concave down. Those do not have an inflection point.
Okay.
So do you want us to do 27?
Yeah, I'm just making sure that one, but I was gonna say, is that one similar to the last one we did? Or the other one that we did with the point?
This 0 to 4 pi is actually the same as saying, like, if it were sine x 0 to pi, they're just saying do it 2 pi. It's saying do it for 1 period.
Okay.
Is all that's referring to. And your instructor on the last exam, he had a lot of fumbles on the exam. So you could see an issue where he doesn't put the right period, and then you're able to take advantage of
Right.
maybe getting some free points there. But you got to take derivatives. So f prime of x derivative sine is cosine. You keep the inside function, then you multiply by the derivative of the inside function. Second derivative is derivative's cosine is minus sine. Keep the inside function, and then you multiply by the derivative of the inside function, which again is 1/2. So your simplified here is -1/4 sine x over 2. You set this equal to 0. So it's where is sine, basically where is sine equal to 0? So where does sine of x equal 0 on the unit circle? Well, it equals 0 at when the y values are at 0 and pi, like that. Now, because it's x over 2, you're supposed to set x over 2 equal to each of those. And then you solve for x again. So x over 2 equals 0 and x over 2 equals pi. because of that x over 2. So then you have x equals 0, 2 times 0 is 0, x equals 2 pi. And those are your two critical points. So it's okay, 0 to 4 pi, 2 pi, and so you have to test pi maybe, and 3 pi, and you're testing that back in here.
Right.
So depending on your comfort level with trig or graphing calculator, whatever. So pi, sine of pi over 2, that's pi over 2 is on the unit circles up here. That's 1 minus 1/4 times 1 is negative. Okay, at 3 pi over 2 is down here. That's -1. Negative times negative is a positive.
Okay, we can go to 33 next.
Okay. While relative extreme of the function is a second derivative, so that's okay. So extremas come from the first derivative. That's what we were working on yesterday. Extrema, min max, relative min max.
Right.
That comes from the first derivative. So could you take the first derivative of this for us, please?
Yeah. 6 minus 2x.
Okay, so set that equal to 0.
And then it just becomes 3. Yeah, 3.
Yep, x equals 3. Okay, so normally, this is what you would normally do, right? You would normally test points, okay? But this problem says to use the second derivative test, okay? Now, I'm not exactly sure how the instructor would make you use the second derivative test on this, but I'll explain to you what the second derivative test is. So you first need, surprise, surprise, the second derivative. So the second derivative is -2, sorry. Okay, and the idea is the following. You test your critical points in the second derivative, okay? So if f double prime of c, so c, imagine c is your critical point, and you could have more than one. If the second derivative is less than 0, that's a max. If the second derivative of your critical point is greater than 0, that's a min. Now, why are they backwards? You can think long and hard about increasing and decreasing, stuff like that, if you really want to, or you can just remember these rules.
Okay.
So you might be wondering, well, what is going on at our critical point where, well, the second derivative is always negative. So at our critical point, the second derivative is negative, which means that this is a max. Okay, now, how can we confirm that otherwise? Well, the original graph, 6x minus x squared, looks like this, so it has a max. If we use the first derivative test and we test points here, we end up getting positive and negative. And we talked about when you go from a positive to a negative, that's a max. And then the second derivative confirms that.
Okay.
So there's a bunch of ways to get to the same outcome.
Right. Okay.
I don't know how the instructor on a multiple choice test can tell you, you must use second derivative test. I wouldn't use it.
Okay.
Because it's more complicated.
Right.
Most of the time.
Okay. And then can we go to number 5? And I realize that it doesn't have the instructions, so I can tell you what that is real quick.
All right, well, let's see. Maybe I can figure them out from years and years of seeing the same questions over and over again. Nope, I have no idea what they want to do. Number 5.
Hold on. It says, oh no, never mind. This is like a match.
Curve sketching, maybe.
Yeah, we could skip that. That's fine because I can just put into a calculator.
Yep.
We can do number 17.
Okay, this is a little bit going back in time.
Is this just the same as finding a limit like we did before?
Kind of, you're supposed to do it slightly differently. So this is not a good question the way it's written. But yeah, like you find the limit as x goes to infinity. You can do it a bunch of different ways. There's this thing called L'Hopital's rule, which is probably where you're getting to, maybe, or to tell. But yeah, the limit here is just 4 because 3 over infinity goes to 0. 4 plus 0 is 4. You could graph it and you would see that the thing, to the right, it approaches 4. Can you tell if this is L'Hopital's rule? L
Let me
apostrophe L'Hopital's, pronounced L'Hopital's.
look real quick. No, that's chapter 8. This is chapter 3.
Okay.
This is limits at infinity, horizontal asymptotes, and infinite limits at infinity.
Okay. Well, we can do more of these, but you should be able to recognize or just graph this and see it. There's no like calculus here. It's just, this is actually pre-calculus stuff.
I was gonna say, if this is just finding limits, I don't need to practice this because I know how to do
I
that.
mean,
already.
we got a few more minutes here. I mean, I recommend doing a couple more just to see if any other
Yeah,
things
that's
come
fine.
up out of this. What's next on your list?
39.
39. Okay, all the way to
Finding
39.
horizontal asymptotes using technology.
Well, you would not use, I mean, if you're
Oh,
using tech,
a graph. Oh, never mind then. Okay,
you can do this by hand, but it's going to end up being, well, it's going to end up being 3, which you might be able to see why,
yeah.
but, these can get more complicated, but they usually are in the realm of like, you gotta do them by hand, so.
Um,
I mean, I see a bunch of these that say use technology. So if you
yeah.
are gonna use your graphing calculator, I would use the table set feature where you ask. There's auto and then ask. And the reason I suggest ask is because then you can put in like 10, 100, 1000, like you can really get a feel for what's going on as it gets large, rather than being unsure whether it does. The other thing is the instructor might give you one that's not like super nice, like where it's like ends up approaching like the square root of 3 over 5, and that's really hard to figure out in a calculator.
Right.
But what do I know? I'm not given the test, so.
And where do I find the ask button on my calculator? Because I don't see that. I'm
Yeah,
using
it's second table set. It's the top there. I think it's under window, maybe. Yes. Let me snip that in here so you can see.
Yeah, because I'm using a TI Inspire CX. So
Oh, well, it's probably more sophisticated. This one, I'm looking, the table set there is what I was referring to.
okay. Okay. I'll look.
That's where you find the ask and stuff. Yeah, it's a good calculator. Probably does too much, but
Yeah, I technically wouldn't be allowed to use it, but he got rid of the lockdown browser. So
great.
yeah. Okay. Well,
Anything
that's
else I can
all.
help you with today?
No, that's perfect.
All right, so we got another lesson tomorrow.
Yep.
Go ahead and stop the recording here. Do you know about your schedule?